You are about to find out that everything you were taught about light is, technically, backwards. Not wrong, backwards. Because here's the claim we're going to prove in the next 20 minutes, and I want you to sit with how strange it sounds before we even start. Light does not travel at the speed of light. Nothing does. Not even light. I know how that sounds. You've heard the number your whole life. 299,792,458 meters per second. It's in your textbooks, it's on the plaques at planetariums, it's the cosmic speed limit every science documentary treats as gospel. And it is real, it is measurable, it is, as far as we can tell, absolute. But that number only exists for you, for us, for anyone standing outside of light watching it go by. For light itself, if light could have a itself, the trip doesn't take any time at all. Zero. Not a fraction of a second. Not a billionth of a second. Zero. In the same way that 2 plus 2 is 4. Not approximately zero, exactly zero. A photon that leaves a star 1,000 light years away and lands in your eye tonight experiences that entire journey, the 1,000 years, the trillions of kilometers, as no time whatsoever. From its own point of view, if it had one, it left and arrived in the same instant. There was no during, there was no journey, there was only before and after, stitched directly together with nothing in between. Stay with me here, because this isn't a metaphor and it isn't a rounding error in a textbook. It's a hard consequence of one of the most rigorously tested theories in the history of science. And once you understand why it's true, you'll never look at the light from a lamp, a phone screen, or a star the same way again. So let's build this properly, case by case, because a claim this strange deserves receipts. Here's where we start. 1905. A patent clerk in Bern, Switzerland, 26 years old, working a day job stamping paperwork because no university would hire him as a physicist. His name was Albert Einstein, and in that year, a year historians of science now call his miracle year, he published 4 separate papers that each, individually, would have been enough to define a career. One explained the photoelectric effect, the discovery that would eventually win him the Nobel Prize. One provided direct evidence for the existence of atoms by explaining the jittery motion of pollen grains in water. One quietly broke the universe in half. The paper wasn't really about light traveling fast. It was about something more unsettling. That time itself is not the same for everyone. That the clock on your wall and the clock on a spaceship moving near light speed do not agree, and neither one is wrong. This idea didn't come from nowhere. It came from a problem that had been bothering physicists for decades. In 1887, 2 American scientists, Albert Michelson and Edward Morley, ran an experiment that should have been boring. They were trying to measure the ether wind. At the time, scientists assumed light needed a medium to travel through, the way sound needs air. They called this medium the luminiferous ether, and they assumed Earth was plowing through it as it orbited the Sun. So light moving with that wind should travel faster, light moving against it should travel slower. Simple. Except when they measured it using an incredibly precise device that split a beam of light, sent it in 2 perpendicular directions, and recombined it to look for tiny timing differences, they found nothing. No difference. None. The speed of light was exactly the same no matter which direction they measured it, no matter what time of year, no matter how Earth was moving through space. This was, frankly, impossible under the physics of the day. It's the equivalent of throwing a ball forward from a moving train and a ball backward from the same train, and both balls somehow arrive at the same speed relative to the ground. Every physicist who heard about this result assumed something was broken. The equipment, the math, the assumptions. For nearly 2 decades, this failed experiment sat there as an open wound in physics. Some scientists proposed that objects physically contract slightly in the direction of motion, just enough to hide the effect, a strange patch called the Lorentz-Fitzgerald contraction, named after physicists Hendrik Lorentz and George Fitzgerald. It wasn't a bad guess, and a version of it turned out to be real, though not for the reason they originally thought. But patch after patch kept accumulating, each one narrowly rescuing the old picture of absolute space and absolute time, each one feeling more like a workaround than an explanation. Physics doesn't tolerate workarounds forever. Eventually something has to give. Einstein assumed something else. He assumed the experiment was right and reality was weirder than anyone wanted to admit. Here's his reversal, and it's the hinge this entire video swings on. What if the speed of light isn't just fast? What if it's the one truly fixed, unbreakable constant in the universe, and everything else, including time and space themselves, has to bend and stretch to keep that number the same for every observer, no matter how they're moving? That single assumption became special relativity, and it's not a fringe idea some scientists still argue about. It has been tested more times, in more ways, with more precision than almost any other claim in physics. GPS satellites have to correct for it every single day, or your phone's map would drift off by kilometers within hours. Particle accelerators confirm it billions of times per second. It is, at this point, about as settled as science gets. So let's actually follow the logic, because this is where it gets strange in a way that connects directly to our claim about light experiencing zero time. Picture two people. One of them, call her the traveler, is on a spaceship moving at 99% of the speed of light. The other, call him the observer, is standing still on Earth watching her go. Both of them are carrying a clock. Simple clocks. Imagine a photon of light bouncing between two mirrors, one on the floor, one on the ceiling. And every time it hits the floor mirror, that counts as one tick. A light clock. From the traveler's point of view, sitting inside her spaceship, her light clock looks completely normal. The photon bounces straight up, straight down, up, down, nothing weird. Her ticks feel exactly like ticks always feel. But the observer on Earth, watching her ship zoom past, sees something different. Because her ship is moving forward while the photon bounces up and down, from his perspective the photon isn't just moving vertically, it's tracing a diagonal path, a zigzag, because the whole clock is being carried forward through space while the light inside it bounces. Here's the part that breaks people's intuition the first time they hear it. The speed of light has to be the same for both of them. That's the whole Michelson-Morley result. Light doesn't speed up or slow down depending on who's watching or how they're moving. So if the observer sees the photon tracing a longer diagonal path, but that photon still can't exceed the same fixed speed, the only way the math can work out is if, from his perspective, more time has to pass for each of her ticks. Her clock runs slow, not because anything is mechanically wrong with it, because time itself, from his frame of reference, has to stretch to keep the speed of light constant. This is called time dilation, and it isn't philosophical. It isn't a trick of the light itself, some observation after effect where light physically changes when you look at it. Nothing about the light's physical wavelength or energy is at stake here. This is deeper than that. It's baked into the actual structure of space-time. And we've measured this directly, in ways you'd never expect. In 1971, physicists Joseph Haefel and Richard Keating put atomic clocks, the most precise timekeeping devices ever built, on commercial airplanes and flew them around the world, once eastward, once westward. Then they compared those clocks to identical atomic clocks that stayed on the ground. The flying clocks came back reading different times than the stationary ones. Not by much, nanoseconds, but exactly to the level of precision science could measure, matching what Einstein's equations predicted decades earlier. There's a more dramatic version of this happening constantly, above your head, right now. Cosmic rays hitting our upper atmosphere create particles called muons. Muons are famously unstable. They decay, on average, in about 2.2 microseconds. That's such a short lifespan that even traveling near the speed of light, basic classical physics says most muons should decay long before they ever reach the ground. But they don't. Detectors at sea level catch far more muons than that simple math allows. The reason is time dilation. From our point of view on the ground, the muon's internal clock, the process that governs its decay, is running slow because it's moving so close to light speed. It survives longer than it should, long enough to reach us, precisely because time is behaving differently for something moving that fast. There's one more piece of evidence worth putting on the table before we push further, because it's the version of this idea most people have actually heard of, even if they didn't know the mechanism behind it. The twin paradox. Imagine identical twins. One stays on Earth, the other boards a spacecraft, accelerates to a significant fraction of the speed of light, travels to a distant star, turns around, and comes back. When the traveling twin steps off the ship, she is measurably younger than her sibling who stayed behind. Not figuratively, actually younger, biologically, by an amount that can be calculated precisely from her speed and the duration of her trip. For decades this was framed as a paradox because people assume both perspectives should be symmetric. From the ship, isn't Earth the one that moved away and came back? Shouldn't it be the Earth twin who ages less? The resolution is that the situation isn't symmetric at all. The traveling twin is the one who accelerates, decelerates, and turns around, while the Earth-based twin stays in a single, unchanging reference frame the entire time. That asymmetry is exactly what breaks the tie, and modern experiments with high-precision atomic clocks flown on aircraft, including follow-ups to the original Havlik-Keating flights, have confirmed the effect lines up with the predicted numbers to a remarkable degree of accuracy. This isn't a thought experiment anymore. It's been measured repeatedly on Earth. Now here's where we push this to its absolute limit, and where our headline claim stops being a curiosity and becomes almost unavoidable. Time dilation isn't a fixed penalty. It scales with speed. The faster you go, the more extreme the stretching becomes. There's an equation for this, the Lorentz factor, and you don't need to memorize it, but you do need to understand its shape. As your speed gets closer and closer to the speed of light, this factor doesn't increase gently. It shoots upward, faster and faster, approaching infinity. At 10% of light speed, time dilation is barely noticeable. At 50%, it's measurable but modest. At 99%, a year on your ship might correspond to 7 years back on Earth. At 99.99%, that gap stretches even further. Keep pushing the speed higher, and the amount of time passing for the traveler relative to everyone else keeps shrinking. It never quite hits zero for any speed less than light itself, but it gets arbitrarily close. So now ask the question the entire physics community has had to sit with since 1905. What happens at exactly the speed of light? You already know the answer, because I told you at the start. Time dilation becomes total, complete. The traveler's clock doesn't just run slow, it doesn't tick at all. Zero elapsed time. Not a very small number. Zero. This is why physicists say light experiences no proper time. Proper time is the technical term for time as measured by something moving along its own path, from its own perspective, like the traveler's wristwatch on her own ship, not the observer's clock watching her go by. For literally everything with mass, you, me, a spaceship, a muon, proper time always ticks forward, just at different rates depending on speed. But for light, which has no mass, the math doesn't just slow proper time down, it collapses it entirely. This is the reality check moment, and I want to correct something before it curdles into the wrong idea in your head, because this is exactly where most explanations of this topic quietly get it wrong. The myth version of this fact says, light experiences time so slowly it's basically frozen. That sounds close, but it's not accurate, and the distinction actually matters. It's not that light experiences time very slowly, the way an extremely dilated clock might tick once a century. Zero isn't a very small positive number. It's a mathematical wall. Special relativity's own equations become undefined, literally divide by zero undefined, if you try to plug in the speed of light as something with a proper reference frame at all. Which leads physicists to a conclusion that sounds almost like a technicality, but is actually the whole point. Light doesn't have a valid reference frame. You cannot ask, what does the universe look like from light's point of view, because the question itself breaks the math that would answer it. It's not that light experiences the universe instantaneously, exactly. It's that light's experience isn't a coherent concept inside the theory that describes it. The instant travel description is the closest human language and human intuition can get to expressing what the equation actually say, which is that the concept of elapsed time simply does not apply to something moving at that exact speed. That distinction is why this fact resists being sensationalized into nonsense, and why it stayed a genuinely open, respected topic of discussion among physicists rather than pseudoscience. It's not mystical, it's a boundary condition in a theory we've tested to extraordinary precision, sitting right at the edge of where our normal intuitions about time simply stop working. Now here's what should be bothering you, because it bothered me the first time I actually worked through this, and I think it should bother you too. If light experiences zero elapsed time between emission and absorption, then in what sense does light travel at all? From our side of things, the observer's side, the side every human being who has ever lived experiences, light absolutely travels. It takes 8 minutes and 20 seconds to get from the Sun to Earth. It takes 4 years and 3 months to reach us from Proxima Centauri, our nearest stellar neighbor. It takes over 2 million years from the Andromeda galaxy. These aren't approximations. They're precisely measured durations, confirmed by everything from radar ranging to the redshift of distant galaxies. Light traveling is one of the most well-established facts in all of science. But traveling implies a journey with a beginning, a middle, and an end. Implies that something is happening during the trip. And for light itself, there is no middle. There is no during. Emission and absorption are, from the only frame of reference light could theoretically be described in, the same event, separated by zero time. The middle 1,000 years of travel that we observe simply isn't there for light, because for light, there and here, the star and your eye, are effectively directly connected, with nothing in between. This is the part where I want you to actually sit with the scale of what that means, instead of just nodding along. Every star you've ever looked at in the night sky, you're seeing light that, from your reference frame, left that star years, centuries, sometimes millennia ago. You are looking into the past every single time you look up. That much you might already know, but now overlay the other half of this fact on top of it. From the light's own accounting, if such an accounting could exist, none of that time passed at all. The light that left a star 1,000 years ago and is entering your eye right now didn't experience a 1,000-year wait. It didn't experience anything in between. As far as the physics can coherently describe it, the emission and your perception of it are the same instant, joined with nothing intervening, even though for you, standing here on Earth, a full millennium separates those two events. Both of these things are true simultaneously, not one or the other, both. That's not a contradiction, it's the entire point of relativity. Different observers, different valid descriptions of the same events, and no single one of them is more real than the other. The 1,000-year journey is completely real for you. The zero-time connection is completely real for light. Neither cancels the other out. And this isn't just a curiosity confined to some abstract corner of physics. This has teeth in the real world right now, in systems you rely on every day. GPS satellites orbit roughly 20,000 kilometers above you, moving at around 14,000 kilometers per hour. That's nowhere near light speed, but it's fast enough that time dilation from special relativity, plus an opposite effect from general relativity caused by weaker gravity at that altitude, genuinely shifts how fast their onboard atomic clocks tick compared to clocks on the ground. If engineers hadn't corrected for this, calculated directly from Einstein's equations, GPS positioning would drift by several kilometers within a single day. The entire system, the one routing your rideshare, guiding commercial flights, syncing financial transactions down to the millisecond, only works because we've taken this exact light and time behave strangely fact and turned it into an engineering correction applied automatically every day to keep your phone's blue dot accurate. So when someone tells you relativity is just abstract theory with no real-world consequence, you now have the receipts to push back. It's in your pocket, it's in the plane overhead, it's in the timestamp on your bank transfer. There's an even more extreme version of this same effect, one that takes us away from satellites and into some of the strangest objects in the universe: black holes. Imagine watching a friend fall toward a black hole's event horizon, the boundary past which nothing, not even light, can escape. From your point of view, watching from a safe distance, you would never actually see her cross that boundary. Her image would appear to slow down more and more as she approached it, her light stretching and dimming, effectively frozen at the threshold forever, at least as far as your observation is concerned. But from her own perspective, on her own clock, she crosses the horizon in a perfectly ordinary, finite amount of time and continues onward. Two valid descriptions again, hers and the outside observers, both real, both consistent with the same equations, both refusing to agree on when or even whether a single event actually happened. It's the same family of effect that gives us light's zero proper time, pushed to its most dramatic, gravity-warped extreme. And it's a direct prediction of Einstein's later work, General Relativity, which built directly on the special relativity we've been walking through. Now let's push one level further, into the part of this that even physicists find genuinely uncomfortable to sit with, because it touches something even bigger than light, causality itself. If two events can be connected with zero elapsed time between them, from some valid description of reality, doesn't that threaten cause and effect? If light experiences no time, could information somehow travel instantly, breaking the strict ordering of cause before effect that the entire universe seems to depend on? Here's the careful answer, and it's important to get this exactly right, because a sloppy version of this claim genuinely does slide into pseudoscience. The zero proper time fact does not mean light can be used to send information instantly to some other point, and it does not create loopholes for faster than light communication or causality violations. Every outside observer, every reference frame that isn't light itself, still measures light taking a specific, finite, calculable amount of time to get anywhere. The speed limit for cause and effect, as experienced by literally everyone capable of observing it, remains absolutely intact. What's strange is confined entirely to the internal, almost unanswerable question of what light's own perspective would be. And the honest scientific answer is that light doesn't get a perspective. The instant travel description isn't a backdoor around the speed limit. It's a description of why the speed limit exists in the first place, expressed as a boundary the equations themselves refuse to cross. This is the human cost worth sitting with, even in a topic this abstract. Physicists spent the better part of a century getting comfortable with the idea that the universe simply doesn't owe us an intuitive answer here. Einstein himself wrote, in letters to colleagues, about wrestling with exactly this kind of implication. Not because the math was wrong, but because human intuition, built entirely from experiences at ordinary, slow, everyday speeds, was never designed to make sense of what happens at the edge of the universe's actual speed limit. Some of the physicists who worked out these consequences in the early 20th century described feeling less like they were discovering a fact about light, and more like they'd discovered a fact about the limits of human intuition itself. There's a related mystery worth addressing directly, because if you've spent any time in physics content online, you've probably heard the word entanglement thrown around, alongside claims about instant connections across the universe. And I want to be precise about where that fits, because it's genuinely a different phenomenon, and conflating the two is one of the most common myths in this entire space. Quantum entanglement lets two particles share a correlated state, such that measuring one instantly tells you something about the other, regardless of the distance between them. That sounds, on the surface, like the same kind of instant connection we've been describing with light's zero proper time. It is not. Entanglement correlations cannot be used to transmit usable information faster than light, a limit called the no communication theorem, and it's been checked rigorously. You cannot use entangled particles to send a message, a warning, or any decodable content instantly across space. What's correlated is not a signal, it's a statistical relationship that only becomes meaningful once you compare results through an ordinary, light-speed limited channel. So entanglement spookiness, as Einstein famously and skeptically called it, is a genuinely different mystery from the one in this video, even though pop science content frequently blurs them together into one vague idea of quantum instant connection. Light's zero proper time is a direct, well-understood consequence of special relativity's mathematics. Entanglement is a separate, equally real, but mechanically distinct piece of quantum mechanics. Keeping those two straight is exactly the kind of distinction an evidence-first breakdown owes you. That's really what this whole video has been circling. It's not really a fact about light. It's a fact about the structure of time, and light just happens to be the one thing in the universe that sits exactly at the edge where that structure becomes visible. So where does this leave us? We've done the case file work. Michelson and Morley found the anomaly. Einstein reframed it. The light clock thought experiment shows exactly why moving clocks run slow. The muon experiments and the flying atomic clocks confirm it in the real world repeatedly, precisely. The Lorentz factor shows the trend accelerating toward a boundary at light speed. And at that boundary, the equations don't describe very slow time. They describe the total absence of elapsed time, a limit where the very concept of a light's eye view stops being definable. Nothing travels at the speed of light, not even light, because for light, traveling isn't the right word for what's happening at all. It's less a journey and more a direct connection between 2 points, stitched together with zero time in between, even while every observer outside of that connection watches it take exactly as long as the distance and the universal speed limit demand. Think about how quietly radical that is. We spend our entire lives assuming time is the one thing everyone shares equally, that a second here is a second everywhere, that now means the same thing to you and to someone standing next to you and to someone on the other side of the planet. Relativity doesn't just complicate that assumption, it dismantles it completely, and it does so using nothing more exotic than a beam of light bouncing between two mirrors and some careful algebra. That's the part that should genuinely unsettle you a little. This isn't a fringe interpretation debated by a handful of theorists. It's the operating manual for a universe that has been checked against reality thousands of times, by aircraft, by satellites, by particle accelerators, by astronomers watching binary star systems slowly spiral toward each other exactly as predicted, down to the fraction of a second. Here's what I want to leave you with, because it's the thread we're going to pull on next. If light experiences zero time between its emission and its absorption, that raises an even stranger question we haven't touched yet. Does light experience distance at all? If there's no time passing, is there any meaningful sense in which light crosses the actual physical space between a star and your eye? Or does the entire concept of distance, from light's impossible to define perspective, collapse in exactly the same way time did? That's not a rhetorical flourish. It's a real open thread in how physicists think about the geometry of spacetime near the speed of light. And it's exactly where we are picking this up next time. If this kind of case file breakdown is the kind of thing you want more of, evidence first, myth corrected, receipts shown. The biggest thing you can do is leave a comment telling me which part of this actually changed how you think about light, because that's genuinely what tells me which mysteries to chase down next. And if you want to directly support the research time that goes into pulling primary sources, like the original 1887 Michelson-Morley papers, and cross-checking every claim before it makes it into one of these scripts, a super thanks goes a long way, and I read every single one. Until next time, keep questioning what looks obvious. It usually isn't.